Welcome, my dear friends, to my YouTube channel. Now, yesterday's lecture, I shall discuss about artificial satellite. Okay, and we have find out the orbital velocity and time period of revolution of an artificial satellite revolving around the Earth. Okay, so there we find that the orbital velocity of an artificial satellite can be written in this way: r root g by r plus h. Okay, and the time period of revolution can be written in this way: 2 pi by r square root r plus h whole cube by g, where we take r is the radius of Earth and h is the height of the satellite from Earth's surface. Okay, now first of all, here we shall discuss about a special case, that is, if the satellite is very close to Earth's surface, then what happens. Okay, so when the satellite is very close to Earth's surface, then what approximation we are going to use? That means h is very small. That means we take r plus h, this term almost equal to r, since h is very small. So if we substitute this approximation in equation 1, then what would be the result? We get r, we substitute r instead of r plus h. So this is the result. So if we simplify it, we get it this. Okay. Now more commonly, if we substitute these values, then 9.8, and this is 6400 kilometer into 10 cube, this is meter. So the unit will be meter per second, and almost this is equal to 7919 meter per second. So this is the orbital velocity of an artificial satellite that is very close to Earth's surface. Okay, so this is the orbital velocity. Now if we substitute this value in the time period of revolution, that is to find out the time period, then what will be the result? That will also we find. So simply the expression of time period is this: 2 pi by r square root of r plus h whole cube upon g. So simply we put this r cube. Okay, so simply it would be 2 pi square root r by g. Okay, so if we substitute these values, then what we get? R will be 6400 into 10 cube by 9.8. So this will be almost this. Okay, approximately equal to this second, which is almost equal to approximately 84 minutes. Okay, almost equal to 84 minutes. So this is the expression of time period of revolution, provided that the satellite is very close to Earth's surface. Okay, now our second issue in today's lecture, we will discuss a special type of satellite which is called geostationary satellite. Okay, this is called geostationary satellite. Geostationary satellite. Okay, geostationary satellite. So under what conditions a satellite is called geostationary? First of all, you have to consider the orbit as circular. The orbit must be circular. But while doing the general case of artificial satellite, I take the example of simple circular orbit, but you can also take elliptical orbit. For simplicity, I take circular orbit, but the orbit must be elliptical. Okay, but in case of a geostationary satellite, the orbit must be a circular one. Okay, and the satellite revolves around the earth, revolves around the earth with same velocity. The satellite revolves around the earth with same velocity as earth does about its own axis. Okay, we all know that the earth has a speed motion, that's why it rotates around its own axis. So the velocity will be same and equal to the velocity of the satellite that is rotating around the earth. Okay, that means orbital velocity of a geostationary satellite must be equal to the velocity of the earth when it rotates about its own axis due to spin motion. Okay, so under these conditions a geostationary satellite is called a artificial satellite is called geostationary satellite. A satellite is said to be geostationary if it satisfies these two conditions. Okay, now let us try to find out the height at which a geostationary satellite must be placed so that it can work properly. Say this is earth and say this is a geostationary satellite. This is the radius of earth and this is suppose the height of the geostationary satellite. Okay, so we all know that m represents the mass of earth, r represents the radius of earth, and v say mass of the geostationary satellite we took mg, that means mass of the geostationary satellite. V is the orbital velocity of the geostationary satellite and h is the height from Earth's surface. Okay, the height of the geostationary satellite from Earth's surface, this is h. So, and we also take this distance, r plus h is equal to small r. Okay, small r. Okay, so what would be the force of attraction between Earth and geostationary satellite? Force of attraction between Earth and geostationary satellite. Okay, so force of attraction between Earth and geostationary satellite. So what would be this? If you denote Fa, that is G, mass of Earth, mass of geostationary satellite, by r plus h whole square, simply you write small r square. Okay, so this is the force of attraction between the Earth and the geostationary satellite. Okay, so this is one. Now the geostationary satellite is rotating around the orbit, so the motion is rotational motion, so there will be a centrifugal force, fictitious centrifugal force exists in the motion, so due to the own motion of the satellite. Okay, so due to the own motion of the satellite, the centrifugal force on the satellite, say Fc, mass of the satellite into its velocity by r, and r means small r. Okay, so this is the centrifugal force due to the own motion of the satellite. Centrifugal force, that is this pseudo type of force only exists in rotational motion. Okay, not linear motion. Okay, I will tell about this type of forces in rotating frame of reference chapter in classical mechanics. Okay, so this is the centrifugal force. Now we all know the orbital stability condition, okay, from which we can calculate the velocity. First we have to find out the velocity, then time period. So the orbital stability condition is that centrifugal force balances the force of attraction, gravity force. So simply mg into v square upon r, this is simply g into m into mg upon r square. So mg cancels, so v square, this is simply gm by r. And again we know the acceleration due to gravity at the surface of earth, this gm by r square. So from which we can write gm as g into capital R square. Remember that this formula is only valid if a body is located at the surface of earth, okay. So you can put g into r square by r. So what will be my orbital velocity? That is simply r root g upon r, okay. So this is the orbital velocity of the geostationary satellite, which we require to find out the time period of revolution, because time period of revolution is nothing but the circumference of the orbit divided by velocity. So at first we have to find out this, okay. So my health is not so well today, that's why I speak slowly. So the time period of revolution, that would be 2 pi r by v, okay. So what I find, v is square root r root g by r. So if we substitute this, then we get this r by g, okay. This is the time period. So if we take square, okay, just I do one step, this is simply r cube by g. So if we take the square, that is t square, this is simply 4 pi square by r square into r cube by g, okay. Now from which you can easily write r as g into r square into t square by 4 pi square to the power 1/3. Now by substituting these values, you can easily calculate the value of r, which is required to find out the height of the satellite, okay. So if we substitute these values, that is r, we take 6400 into 10 cube meter, we take t. As the earth rotates around its own axis by 24 hours, we take 24 hours. That means this second, okay. 24 hours, that means 24 multiplied by 367. So if we substitute these values, then the value of r almost become this in kilometer, okay. Okay, the value of r becomes this. So with the help of this value of r, we can easily find out the height at which the geostationary satellite must be placed so that it can work properly. This is a very important question. Now we all know that r, this is simply r plus h. So what will be the h? That is simply r minus r. So this is, we found this, and radius of earth is this. So this is in kilometer. So this is the result, okay. So this is the result. So a geostationary satellite must be placed at a height 36,000 km from earth's surface so that it can work properly, okay. And again, previously we see that t square is also proportional to r cube. That means like an ordinary satellite, a geostationary satellite also obey Kepler's third law, okay. So what we conclude? So what we conclude? We conclude that a geostationary satellite should be placed at a height. Okay, a geostationary satellite should be placed at a height 36,000 kilometer. Okay, should be placed at a height 36 kilometer from Earth's surface. Okay, so a geostationary satellite should be placed at a height 36,000 kilometer from Earth's surface so that it can work properly. So that it can work properly. Okay, so dear guys, this is what about geostationary satellite. Now in our next class I shall going to discuss the binding energy of an artificial satellite and escape velocity. Okay, that I will do in my next lecture. So if you don't subscribe my channel, then just subscribe it and share it to your friends. Okay, and link of this video will be given in the description box. If you have any query, then just write it in comment section. Okay, so thank you.